Hi, everybody, and hopefully you all can see me. I'm Faraz, and we're going to be starting Speakeasy JS right now. So just wanted to give a little backstory on what caused the genesis of this event. So I was talking to Mikeal Rogers, who's going to be one of our speakers today, and we were just brainstorming what to do to encourage more people to build stuff. And build cool stuff, especially mad science, experiments, stuff that's more than just your typical React app. And we had the idea to do this conference, and we're going to hopefully be doing it every Friday, and we'll see if it can become a thing. Yeah, I just wanted to say, there's nothing wrong with doing coding for work and for web apps and for getting paid and consulting and whatever kind of normal stuff you got to do to make the ends meet. But there's a special place in my heart for coding for its own sake and coding for the sake of just proving that you can do something. And I think the JavaScript community in particular is really a place where that happens quite a lot. And I think some of the most innovative ideas that we use in this space, in JavaScript and on NPM, have actually come from people just hacking around and just trying to make something that works. And so, just make something that gives them joy, really. It's like the idea of I bet that we could do this. I bet that we could, make this thing work and do it in JavaScript, and everybody else saying, no way, that's a terrible idea. I don't think that could work. And then somebody persisting and saying, I'm going to prove you wrong. I'm going to put JavaScript on a drone, or I'm going to make a torrent app in the browser, or I'm going to put JavaScript on a robot, and I'm going to make JavaScript do talk over a serial protocol, and we're going to build peer-to-peer networks using JavaScript. And everybody who was ever saying in the past that is a bad idea has been proven wrong, again and again and again. And so hopefully this can be a space for people to do those kinds of experiments and then to share them with people and to get other people excited. And so anyway, that's kind of the idea. And yeah, I'm excited to see what happens. So without further ado, let us connect Mikeal in here. So let's see here. Where is Mikeal? We got to figure out some of our tech stuff here. So Mikeal, there you are. Gotcha. Boom.
Hello.
Okay, Mikeal, say hello. You're on the air.
Hey everybody, how y'all doing?
So there's gonna be no audio feedback, right? It's not a live audience other than me. So I mean, we can put Mikola in here. If you want to say hi, Mikola, you're here ready to go too.
Hello, I had to unmute my microphone, but I'm here.
Cool, but yeah, go ahead and take it away, Mikeal.
All right. Yeah, so this is a project called Z-DAG. I had the idea for this a few weeks ago, and I've been coding it. So well, you're going to see some of it works, some of it hasn't been implemented yet. But the ideas are really sound, and it's a really cool approach that I'm excited about. So let's just get into it. JSON++, that sounds like something you invented. So yeah, that's not, but it kind of gets to the heart of what I'm talking about here. So this format is a binary format. So it has all the JSON types plus inline binary, because if you're already a binary format, why not? Only reason JSON doesn't have binary is because it's a string format. So you get all the JSON types. You can do anything you would normally do with JSON with Z-DAG, but you also get the binary type. And also, if you want it, you have this link type. And the link type is actually really cool. You can, the hash link, it's like a native hash link type. And so if you have different encodes of different pieces of data, you can actually link to them by hash. And it's this, it uses CID, the specification from Mikeal that allows you to really link between different formats. So you could have different pieces of Z-DAG data linked to each other, but you could also link to JSON data or to IPFS or Bitcoin or Git or whatever. Anything that has content addressing. So, a lot of people aren't familiar with this type. I don't want to downplay it. It's actually really cool, and you can do a lot of really amazing stuff with it. But it's really like a whole other talk to talk about what you could do with hash link data structures. This talk is mostly just about Z-DAG and about the compression stuff side of it. So real quick here, you're really going to need to know about varants to understand this. So varants are variably sized integers. So, in your programming language, if you've got an integer, it takes up usually like a fixed size of memory. So if you've got a 64-bit integer, that means that it takes up 64 bits. And so if it's a 0, then it's going to still take up 64 bits. If you're trying to create a format that's relatively small in size, you want to try to get the size of numbers down to their minimum viable size, right? So varint is this way for you to write numbers, and they can be kind of a variable size, and the smaller the number is, the less that it'll take. So the important thing to note here is that numbers 127 and below only take up 1 byte. And then they kind of go up from there and they take up more space. And then as you're thinking about kind of like how compression works here and how some of the different stuff works, just remember that small numbers use less space. So if we can get we can literally get the number down to a lower number, it can often be smaller. In the format, we tend to inline these as numbers. We'll talk about that a little bit later. But we'll start talking about tokens at some point and our tokenization of different structures. And in this format, what we use for tokens are just numbers between 98 and 127. And so those are high numbers in the varint range, but they're also, if you ever use like a uint8 array in JavaScript, you'll get back a bunch of numbers for binary, and it's just those numbers are the tokens, essentially. So this is how most people use compression, right? Like you take a picture, you take a video, and then you hand it to a compressor, and it makes it smaller. And you don't really like go back and forth with the compressor much. You don't alter your photo to match the compressor. Data structures are a little bit different. Like JSON data, we make JSON data. We get to shape it and change it, and we can actually have a very different relationship with the compressor when we're programmers than we do with generic string compression and stuff like that, where it's very opaque and we just kind of hand it data. We actually have the ability here to offer some features to developers. The developers can potentially like use to even maximize their compression rate. We don't need to be in this really one-directional relationship with the compressor. So as long as the rules are really simple, right? If we can get our head around these compression rules, then anybody can very easily kind of maximize their rates. And you can think about this when you design your data. So there's really just kind of 3 classes of compression techniques that I'll talk about. One is deduplication, pretty obvious. Don't do something twice. If you're going to write it once, then write references back to the thing. Delta encoding. Delta encoding just means when we have 2 numbers and they're related, if we can write the difference between the numbers rather than the whole numbers, then that means that those numbers will be smaller. And since we're using varint, the smaller numbers are going to take up less space. Another thing that I'll talk about here is called detokenization. So basically, you have a bunch of tokens that tell you about structures. And if you can find really common patterns in the structure, then you can use different tokens to describe the pattern rather than every little piece of data. And then that allows you to remove a lot of bytes from that tokenization. Let's get into what this format looks like. So unlike CBOR, unlike JSON, it's not a linear encode. So it's not, a bunch of inline values with different tokens. We actually take the whole structure that you encode and we break it into 3 parts. So the first part is all those hash links, for a couple of reasons. One is that, they have really well-known parsing rules. So we can actually, line them up really easily without any extra bytes and compact them all together. And we can even shave a lot of these common prefixes. So, these links aren't just hashes. They say what kind of they're linking to, and they say what kind of hash that it is. So if we can, deduplicate those prefixes, then we're going to get the size really far down. The other cool thing about putting it up front is that if we just want to know what a piece of data is linking to, we can just parse that out real quick. Then we're going to take all the values. So your map keys, your string values, your byte values. We're going to take all those and order them, and we're going to put them linearly into a compression table. So this is so that when we do the structure here, we're just going to point back to those points in the table. So this sort of hello world, world hello is about half the size of what it would be in JSON, because we're only writing hello and world once, and then we're sort of linking back to those structures, right? Another really cool thing to think about here, this is where all the string data ends up, right? It's all in this little value setter here, which means that we're not like competing with gzip or deflate or brotli or anything like that. Like if you've dealt with compression a lot, you should not double compress your data. You shouldn't like compress it once and add a bunch of noise and then try to compress it again. But with our compression, we're doing everything in the structure. All the compression that I'm about to talk about is down here. And so we've actually taken all of that string data and put it in a nice, neat little spot for you to still use gzip on or still use brotli on. So we have, you can use a variant codec to do that. You can, if you have these in common storage, you could just compress them there. So there's actually opportunities to leverage all the great string compression libraries that we have around. We're not bouncing out of that because we have a compressed format. So that's really cool. So let's look at a structure and see what we can kind of turn it into. So in our system, we need to tokenize this, right? We need to create tokens for all the structure and like that. So first we got to open and close everything. So all these lists and maps, we got to open and close them. Then we got to have all these typing tokens. The typing tokens are going to say, like, this is a string, this is bytes, this is an integer, right? And then we're going to be pointing back to that compression table, or we're going to be saying, this is the number that it is, right? And then for constants like true and false and null, we have some tokens specifically for those values then. Okay, so this is a fair amount of data. Let's see if we can get this down. Let's look at some of these cool compression techniques that we've got. All right, so first of all, map keys. Map keys are only really one type, right? Like you can only have one type in JavaScript. You can only have one type in JSON. A lot of programming languages actually only support one type for their map keys. So in our data model, we just say, you know what, all map keys are strings. We're just going to shed all these typing tokens and get rid of them because, we're unnecessary. We already know that this is a map, so we know that things always can be a string. We also have, these typing tokens for integers. But because we're using tokens that are in the varant range, they're basically really low varant, we only have to use this typing token when we conflict with that token range. We can actually just inline these values without a token. That's really cool. Now, maps are really interesting, right? One of the things that I think about a lot, and that like my group and my company think about a lot, Protocol Lab, is like what data looks like after you hash it. Because you want, if you hash data once, you want any other data to match that hash. So if you've been using JavaScript for a while, you know that maps are ordered based on how you insert data into them. So if one person has the same map as you have, but they happen to insert the keys in a different order, that'll look differently if you were to just serialize it. So something that we want to do is we want to make all of these hash consistent. So we need stable ordering rules for these map keys here, so that they're always the same. Since our value table, our compression table for the values, is already strictly ordered, we can just leverage the ordering there. So we can just say, oh, well, just only have these map keys increase, from their values over there. Then we can use delta compression. So we can say, oh, instead of encoding the actual pointers, we can encode the difference between the different pointers. The really cool thing here, though, is that we can now use 0 to close out the structure. So we have a different token here for empty maps. So if you open a map, you can use 0 once as the first thing, and that's the only time that it ever is valuable. And then you're only increasing integers over time. And if you ever tried to repeat, you would end up encoding a 0, and then you'd close the structure. So something cool about that, we do a lot of work actually when we write data on top of Seaboard, on top of JSON, to verify that these maps are strictly ordered. But here we don't have to do that. The decompression algorithm is actually validating that these are all really consistent for us. So it's kind of nice. We're opening and closing a lot of structures here. And they're the same structures of the same size. So that seems really wasteful. So something the compressor looks for is whenever you've got a list, and inside of that list, all of the maps or all of the lists are the same size, it's just going to open that structure with a different token called a table token. And then it's going to encode the vectors of the structure into it. And this is actually really common, right? Like if you import a CSV or you import like all these different data types, you're going to end up opening and closing all these structures that are the exact same size all the time. So here, we get to encode the vectors here. And then we also get to shed the final token for even closing out the structure because we know that it's this fixed size. So that gets rid of a lot of tokens for us. It's really nice. Typing tokens take up a lot of space. One of the things that Z-DAG looks for a lot are common patterns in typing. So if you have a map or a list and all of the values in it are the same type, it'll actually use a different token to open that list that says, oh, this is a list and everything in it is this type. So then you don't have to type every single value and you get rid of all those tokens. Something very similar happens if you just have a bunch of types next to each other. So you've got a big list or a big map and you do like, 7 strings in a row. It'll just encode kind of an opening and closing type range into that so that, you're getting rid of a lot of those tokens. When we're in this table token routine here though, we can actually look at it in terms of columns. And we can say, oh, are all the columns of a similar type? Because that seems to happen quite a lot. And here you see that we actually do have really consistent typing for all these comments. So we can just take that typing information and put it into the table. So we said, this one's a string, this one's untyped, and this one is another string. And we say that those numbers are untyped because we don't actually shed any typing tokens saying that it's a number, so we don't. Next here is that we've all, the delta compression is really nice, but we're still encoding the same thing over and over again. Every single one of these maps is the same thing. So when we see that in the table routine, we just say, oh, okay, we're going to encode all that data up into the table, get rid of that as well. So as you can see, this is a lot smaller than it used to be. This is going to take up a lot less bytes. And before you say like, oh, like this is an example that you kind of tailored to this, like, yes, absolutely it was, but that's kind of the point. Like the relationship that we have with this compressor is that we can shape our data to fit it. We can move our types around a little bit so that they take up less bytes, and we can, really compact all of our representations down. And we can even start to do things that we wouldn't have thought about doing in other systems, right? Like this is a very like this structure uses a lot of extra bytes, right? If you were to encode this in JSON, it would be really, really big. But here it's not, and so we can actually kind of make data structures that might be a little bit nicer to use, and they'll still end up being really small. Or, there's some tricks in here, like if you keep the compression table 255 or below, all the pointers will only be 1 byte. And so if you're using a table like this, and you know that, and you've kept that compression table down to 255, you would actually be able to skip around in this structure without fully parsing it, right? You would actually know the exact position in the uintate array for any of these values, which would be really kind of cool. And so you can actually, think of it even in terms of like building additional layers of parsers that are even more efficient if you really wanted to get into it. But yeah, this is really new, so I haven't quite done that yet. But if you want to check it out, look at, some of the docs that are there. I'm working on the spec a little bit, iterating on it. It's going to break all the time. It's very new, but, love to have you checking it out. That's the URL for it. And now I guess I can throw it back to you, Carl.
Cool. Thanks, Michael. That was amazing. So I had a question I wanted to ask. So did I get that right? Did you say something about zero or null terminated object like data structures? Are you trying to bring back null terminated strings, like C style?
Well, look, you've got to have a token to close the structures, and zero works really well because if your pointers are numbers and if your deltas are numbers, then you can either offset them by 1 to never conflict with that token, and then you get the whole number range, right? Or, in the maps, we actually know that it can never be 0, and so we can use 0. But there's actually a couple cases in which we don't use 0 to terminate because it doesn't quite work, so we have a token for it.
Cool. We got a question from the chat. What does Z-DAG stand for? What does the name mean?
So DAG stands for Directed Acrylic Graph. It's a very fancy acronym for effectively a Merkle tree with links kind of between things. So what would be a better way to describe it? It's like a tree with deduplication. So branches can point to the same leaf essentially, and then you get kind of deduplication of the structure. So a really strict tree, right, would not be able to do that. But it's a type of hash linked data structure or Merkle tree. Merkle trees are like, if you know anything about how Git is implemented, Git uses a lot of Merkle trees under the hood. All blockchains and blockchain data structures use this kind of stuff under the hood. But a DAG is like a fancy version of that. Another way that you might think about it is that it's a graph, but the links can only go one direction because the way that hashing works is that you have to know the data in order to create the link to it. Right? So you can only create data that kind of moves this one direction kind of upward. And that's what a DAG stands for. And then Z is, the typical way that we say compressing and between things. So, yeah, since it's all compression, I put the Z there in front of it. And it makes it a 4-letter acronym like CBOR and JSON. It seemed to work really well.
Cool. We have another question from the chat. How does it compare to protobufs? I actually had the same question myself. So it seems to me like you were saying the data or the information about the types goes in the representation itself, which I think is different than protobufs, right?
Yeah.
Don't protobufs, like you have to know in advance what the shape is going to be of the object?
Yes. And I mean, like, protobuf is interesting. A lot of people have done a lot of different things with protobuf. And so some of this stuff in different people's like little libraries, they've they found interesting solutions around. But yeah, I mean, you kind of nailed it there. A very important part of hash-linked data structures, right, or any kind of data structure that's hash, is that you can't have external information applied to that data that's going to change it, because then that hash will mean different things depending on which kind of schema that you applied to it, right? So with not just protobufs, but really any format where you have an external schema that you apply, and that's how you get rid of the typing information, doesn't really work well for these hash-linked data structures. That data isn't part of the hash. And so you really need that to be in there. So something like CBOR and JSON actually works a bit better, even though the decisions that those formats make in terms of trade-offs is not great for hash linking. We actually have these codecs in IPLD called ZDAG JSON and ZDAG CBOR, but we do a lot of work on top of them to handle a lot of those trade-offs and to make them really consistent. But it's still quite a bit of work. So it's nice here to have like a format from the ground up, kind of taking those considerations and making those trade-offs instead.
Cool. Mikola, do you have any questions for Michael before we switch to...
I can talk about what happens when you decide you want to do schema. So I'm actually kind of prepared to do the opposite sort of thing, but in a similar style, right? I guess if I do have to maybe make one quick comment, you store all of the value tokens in this like table at the start of each of these data structures. Is there like a significant performance issue if that table gets too big? Do you have like cache issues with indirection or other things going wrong? Or can you just like avoid doing the lookup in the table when you're parsing it or something? I'm just wondering if like, maybe going back and forth in memory all the time slows it down.
Right. So actually, so the table doesn't have the entries along with tokens. The table is just strictly ordered, and then the ordering basically is the keying, right? Because you pointed it with integers. And actually, so it's just a bunch of lengths and then the value, and even the lengths you can delta compress because the ordering is length first. But anyway, but to answer your actual question, so when the table is 255 or below, and remember there's a separate table for lengths than for values, so we get to do this twice. But if it is 255 or below, then that means that all of the pointers to it will be 1 byte integers, right? So we use the whole kind of the whole byte range for that number. Once you go over 255, then we have to use varants to point at it. And since we're using varants, then now the 1 byte range collapses to 127. And so you lose half of the address, the 1 byte address space when the table gets bigger. And then from there, as the table grows larger, the pointers grow larger, right? So that's the trade-off that you make, is that the larger that table becomes, the more expensive each pointer into it is, which is why some of the delta compression stuff is really important. Like for instance, one thing that we do is if the values in your container, so a map or a list, happen to match the ordering of the table, we'll actually encode it with a different token, and then we'll delta compress them to keep them down. So this is actually kind of useful because if you use sets ever in JavaScript, when you serialize them, you always turn them into lists. And so if you just order them right before you turn them into a list, or when you turn them into a list, then you'll get this nice form of compression in there. So there are ways to bring that down, but yeah, in general, if the table gets really big, then those pointers are going to get really big. And especially if you're comparing the size of this to like JSON or to CBOR, then you can end up in scenarios where the table ends up being more expensive if you're not deduplicating, because now the pointers are getting kind of big.
Yeah,
it's just stated you got to try really hard to do that, because the UTF-8 algorithm looks a lot like the varant algorithm in terms of like what you get in 1 and 2 and
This is not quite really the question that I was asking, but I think it's okay. I think we could maybe talk about it another time, like after this. So I think it's okay though, but I get the idea.
Cool.
All right. Well, thanks a lot, Michael. You want to stick around maybe for we're going to be doing a social thing after Mikola's talk. But yeah, thanks a lot for sharing Z-DAG with us. We're going to go check it out on GitHub and see what it's all about by looking at the code.
Awesome.
Cool. Thanks, Michael.
Awesome.
Alrighty. Cool. So yeah, the floor is yours, Mikola. I'm ready to be wowed and delighted. Go ahead and take it away.
Okay, yeah, let's go for it. Let me put 10 minutes on the clock here so I don't go over when I'm talking. Okay, so hello, my name is Mikola. I have done some stuff with JavaScript in the past, although I've basically sworn off GitHub for the last couple of years, so I haven't been too active on there, but I do still have a profile on there that you can check out. And anyway, I'm going to be talking about a project that I think I open sourced maybe back in 2017. So it's a little older, but it's sort of relevant to this. And I think there's some neat ideas here. So hopefully everyone will get something out of this. So let me first put this concept into some context here. So for maybe like the last 2.5 years, I've been working on a massively multiplayer online browser game in China, which is sort of like a Roblox code. So the actual name of this product is called Daima DAO. And I will just kind of do a quick switch on the screen share thing here so that you can take a look at this. And here's basically what it looks like. So this is the main web page, and basically kids can create games. All of this content was created by like random 12-year-olds in China. And basically, I'm going to go enter into this like little level here. So you just click a link. And again, I have to do another like screen share switch because it pops open a different tab here. So I'll just pop in. And so in this game, there's basically a bunch of kids. I got to hide my God mode admin panel there. And you can see that they're all running around. This whole space was created in the web browser. All of the art here was built in the browser. All of the like little programs that they're running are just like little JavaScript things. These particle effects are going on. I don't actually know the rules of most of these games, to be honest. Like they seem to be very fixated on parkour, jumping puzzle type things. I think in this one, they have to like set themselves on fire and jump along these blocks at the top to get to some reward, but sort of like I don't know, some weird thing. There's like a lights out board game here too. I don't even know what's going on with it, to be honest. But yeah, so this is like I'm getting into it.
Oh, sorry, the frame rate's a little low. I don't know if there's another program on your computer.
No. It's not. It's just the stream though. Like
yeah, it's running fine on my computer. The stream. So if you're seeing some jank here, it's definitely the streaming messing it up, right? So I'm actually getting 60 FPS pretty solid on my computer. So I swear it's not my code.
Yeah, I pulled this up on my phone, and it's really impressive. I mean, it's very smooth, actually. So it's definitely really not doing it justice with the stream right now.
Yeah. So, and you know, this game, like typical games, like this is very early right now. So right now this is 7:30 a.m. in Shenzhen. So there's only like 18 or 20 kids or something playing. So it's not like a very large group. But like sometimes these servers, they get very crowded. You get like dozens or, sometimes like 100 kids in like a single game. So it can get pretty chaotic. And so basically, how do you deal with this? How do you handle like making a multiplayer online game like this work in a browser with all of these kids and whatever? And so this is basically what this project that I created back in 2017 does. It's this thing called MuDB, which is the name is some weird thing in Chinese. It doesn't make any sense at all, really. But it's basically a kind of framework for creating client-server applications in JavaScript. And so this can be interpreted very broadly. We use this for network code, but we also use it for stuff like communicating with the user scripts in the game server. So pretty much anytime you have multi-process communication and you typically have like one centralized leader process, this system is pretty great for putting that stuff together. So this is sort of, an attempt in my own sense to like philosophically try to break the rule of making everything decentralized, right? What happens if we just say, okay, forget that. Let's just make a central server and just see how far we can go with client server processes and JavaScript and Node.js. And there's multiple components to this thing. So we have this core protocol thing that allows you to write different like sort of message protocol abstractions, and then you can put them together and compose them in a more modular way. So you don't have to like do your own message dispatch, framework horseshit with, pardon my like language there, but you don't have to like deal with all of this sort of mess of like writing your own dispatchers and putting them together when you're dispatching sockets out. It has its own socket wrappers for basically wrapping like WebSockets in browser, set timeout emulation. You can also fall back to TCP and UDP on Electron or desktop. WebRTC, web worker communication for running like a virtual server or like a local server, and all kinds of other stuff. So there's a bunch of different sockets. And then there's also the serialization stuff, which is what I'm going to talk about today, because I only have 10 minutes to really go into all this detail, and I don't have to go into the rest. And then we have some things for RPC communication, which is maybe a little boring. And then these replicated data structures for doing like peer-to-peer or like real-time collaboration. It's not exactly a CRDT. It's a different kind of thing, but it's not that crazy an idea. I think there's probably systems that work like this, but this is a fairly efficient system. So you can basically use this to make any kind of multi-user editable document. So you can think of it as like real-time tax forms and stuff. And we use this in our editor so that kids can like build the games together. So serialization, this is what I'm going to talk about, specifically the schema stuff that we have. And basically, serialization is a thing a lot of people really underestimate when they're building web apps in JavaScript. I think like the standard practice for most games seems to be just take whatever you have, dump it into a JSON object, and then do JSON.parse on the client and then pull it out and hope everything's okay. As we've already seen, JSON is a pretty bloated format, right? It's like burns a lot of bandwidth. And actually, if you use a lot of bandwidth and you're using WebSockets, that also means you're going to have really high latency in your game, because TCP has head-of-line blocking. So if you have a big undelivered JSON, turd sitting in your pipe, you'll have to wait for that thing to flush through before the rest of your packets come down, right? So it's not so good. Also, spending a lot of money sending like bloated JSON files around gets really expensive, right? And if you're in a kind of low margin market like China, you have to make sure you don't waste a lot of money on things that aren't going to give you a good return on investment. So JSON is kind of a bad format for, bandwidth, right? It's also really slow to serialize it. So, you end up like basically wasting most of your CPU time if you just do everything with JSON, just doing JSON.serialize and JSON.parse. And there's not a lot that the CPU can do to really optimize JSON, because when you get a big JSON string, all you can do is just scan this buffer and tokenize it and parse it and pull all the pieces out and put it back together. And you end up like doing a bunch of redundant memory allocations. You get a bunch of garbage collection that then causes like your process to pause. And so it's not good, right? It just totally kills your performance. And also, when you're doing it, you then have to like basically parse each JSON data structure twice. And so what I mean by that is usually like the JSON itself is some intermediate representation that then has to be unpacked into whatever data structures your game is actually using or your app is using. And when you do that, you also have to do all of these like validation checks, the JSON stuff, to make sure people didn't stash sneaky little messages in there or whatever that can blow up your server in some way. So you have to do all these security things, and that wastes a lot of time and makes your code really verbose and redundant. And it kind of defeats like the whole dream of just having like an automatic serialization thing where you push a button and it works. So yeah, I just went through that, right? So why not JSON? We basically have this little parsing serialization, the bandwidth, and all the garbage, right? And I would say that these critiques also more or less extend to CBOR and BSON, although they do tend to be a little more compact than JSON. They're still quite inefficient compared to what's possible. So, okay, so what's the logical conclusion? Why not do protobufs, right? Well, protobufs, you still have this garbage problem where you unpack them into a protobuf data structure, and then you have to work with this protobuf in your code. And as a result, you end up, like protobufs never stay in one spot in your project. If you start using protobufs in your project, eventually your entire project is going to be protobufs. Every internal data structure in your code will become a protobuf over time. And this will happen to everyone who's using it, right? In fact, I think what Google should really do is, and this is a $1 million idea here, is they should write a language called protoscript, which is basically a language that's just like a scripting language on top of protobufs. Because that's basically what C++ or JavaScript become when you start working with protobufs. You no longer have access to the internal types and data structures in your language, because you end up having to like pervert everything to work as a protobuf in some way. And so it's all protobufs all the way down. And you're now in this weird protobuf hell world, right? Which is like bad, right? Because now you can't use the features in your own language to like write sane data structures. All your data structures have to be warped into a protobuf in some way, or else you end up doing a bunch of redundant memory copies. So that kind of sucks. And then also in JavaScript, there's one other big problem, which is you end up with this really complex build step. And if you're already layering all this Webpack and asset processing things, another additional step with this protobuf makes your development experience exceedingly painful. So you don't get like your types until you change the protobufs and then recompile them in your watch loop. And then the watch loop might get desynchronized, and like your whole development experience is a nightmare, right? So protobufs, there's enough things that are like really painful about working with them in your code. And having to work with protobuf data structures is such a pain in the ass that it's like nice to not do that. So it would be great if we had something that's better. And also, it turns out that fortunately, we can make things that are much smaller and faster than protobufs, right? So this is basically what Mu Schema is. So this is the whole idea of this project. It's very similar in spirit to protobufs, but there's a few key differences. One is that we have this object pooling and C++ style like copy constructor stuff, which is created for every object that you build in this, right? And so this is really important in a game engine where you don't want to leak memory. So you want your memory, your parser needs to basically have like an object pool so that when you do a patch so that when you parse an object, it doesn't allocate like a bunch of memory and then triggers some major garbage collection stuff. We also want to have these like abilities to put maybe more complex constraints on the like data types that we pass, and we could maybe even write those constraints in JavaScript rather than using some other language. And we also want to be able to like make this thing parse into data structures we care about, not some proto shit thing, right? We want like a real like actual data structure or class or something. I guess we also want to get rid of the build step, and we want all of our type reflection and everything. And then finally, we're also going to use this kind of relativistic serialization, or basically like a delta compression. So I'll get into this in a moment, but it's coming up over there. But this all doesn't come for free. There are drawbacks, right? And these were conscious trade-offs that I made at the start of this project, right? So you probably don't want to use this type of approach to serialization in all cases. For example, with hash linked data, this would probably be a terrible idea. This is only optimized for like ephemeral messages where you have control over the deployment of the server and the client, which is exactly what we have here. If your client is not the same version as the server, your game client is just not going to work. It won't even be able to play the game, right? So because these protocols have to be updated in lockstep, it's totally suitable here. Also, there's no delusions that this thing is going to ever work outside of JavaScript or TypeScript, right? So everything here is completely JavaScript. All of the ability to extend it is JavaScript. There is no hope that this will ever possibly work in Rust or C++ or whatever. I don't care. It's not going to happen, right? Like if you want to build in one of those languages, build a new thing. That's not what this project is about, right? It doesn't care about anything other than JavaScript-based serialization. And last, like these things are only going to be working with these client-server type of objects, right? But this is exactly the situation we have here. So this is, to me, acceptable, but it may not be the right thing for every app, right? It's only when you're building these client-server applications full stack in JavaScript, right? Outside of this space, you're never going to want to use this, right? But this is what it does. And if you are doing that, you should seriously consider using this thing. So what do I mean by like the delta encoding or like patch-based serialization? What's this? This is basically a fancy way of saying that delta encoding works. It's a little more general than just like a variant type delta encoding. But if you really think about it, right, like why would we expect we can do things better? Is that basically what we're going to do in this thing, besides having all these like JavaScript-based extension or like the schemas and whatever, is we are going to reformulate the concept of serializing an object as a relative serialization. So whenever you serialize something, you have to specify the thing that you are serializing it relative to. So this is basically like computing a patch, right? If you have like a base object and you want to apply a patch to it, you have to know the base object in advance, and then you basically transmit the patch over the wire, apply it to the base object, and you get something that's a little bit smaller, right? This is like a common practice. If you, for example, want to send a patch into a giant Git repository without GitHub, you would actually just make a patch, put it in an email, and send it over there. You don't send a copy of all your code. You just send only the stuff that changes. And this is a really good idea, right? I mean, there's a very sound information theory argument for why you should do this, which is Bayes' theorem, right? So this HYX thing here is just conditional entropy. This is basically the number of bits that is required to write or to basically serialize the object Y if you know the object X. So this is like number of bits required to reconstruct Y from X, right? And so you can basically prove that, from Bayes' theorem, that the number of bits required to reconstruct an object, if you already know anything at all, X, right? Doesn't even matter if the thing is exactly related to it, is always less than or equal to the number of bits required to just reconstruct Y from scratch, right? And so we're always going to assume that we have some previous message in the queue or whatever, or we've already observed some previous state, and then we can use that to patch it, right? This is a great situation to be in if you just have like a stream of messages coming from a game server to a client and you want to do these reconstructions all the time, right? And we can this is, conditional entropy would be like the exact minimal way to write it, but we can approximate this by only sending the fields, the object that change, and then even when we do that, drill into those fields and then only apply a change relative to them. So if we have like a number, we only have to store maybe how much the number went up or down, right, relative to the previous value. Or if like a field didn't change at all, we don't even have to transmit that. So typically, this is only going to be a very small part of the game state that we have to send at any given moment. So in pseudocode, this is basically what it looks like, right? If you want to compute a patch, you just pass in this diff of A to B, and you get a patch. And then if you take an object A and apply a patch P to it, you get C. And then you have to have this like basic rule that your patch and diff have to obey, which is that if you basically, do this diff of patch or whatever, you get the object that you diffed to, right? So this is like formally, this is what you need, right, in order for this delta encoding thing to work. All right. Now we can recover the original like serialization method from these delta encoding things by basically picking a particular object as an origin. I'm also way over time here, so I'm going to go like a little. But basically, if we pick a given object O as our like base object, then we can always just keep that in mind and then use that for computing our diffs and patches as we go forward. So going through this, the Mu schema gives you a bunch of different primitive types that you can put together in different ways, very similar to protobufs. You get your collections, so dictionaries, arrays, sorted lists, or whatever. You can make structs and tuple types, and you can also have discriminated use. So here's an example of this, and I'm sorry that the formatting totally fucked up here, but it's all center aligned. But basically, when you write a struct, you just construct the object through composition of this recursively. And then TypeScript can figure out builds for this schema and all the properties in it too. So it all just works like out of the box like that.
I think you could start a trend. Everybody should center their code from now on.
Yeah. Well, I wish I could take credit for this idea, but it's this Code EMD thing that I'm trying out that came up with this invention. I don't even know where it got this concept from. It's a great idea, though. It goes straight down the list. It's like Chinese poetry. Okay, so Mu schema extensions here. Yeah, so you can also encode different ways of serializing something into the schema itself. So you could replace a variant with like a fixed size int if you always know it's going to be a uniform value in some range. You can do like Schropel style encoding for negative numbers or relative variants. And you can basically push some of these serialization concerns up to the user level, which is actually good because it's very easy to experiment with them and play around with like different ways to do the serialization and the patching in these structures. And then you can basically see what makes it faster or slower, what uses more or less bandwidth pretty quickly. And then you can also write your own schemas here because these things are just objects, right? Like this is just an object that implements these different places. And then from that, you can basically do whatever you need to do with it. So here's some more stuff. How it's implemented uses runtime code generation to like sort of flatten all the structs out and save space. It also uses memory pooling. to basically reduce the overhead of allocation. There's also a JSON mode that's sort of an optional thing, which you can use. So you can actually make the JSON serialization a little faster. This is used in some RPC stuff. And in the future, like one day, maybe when we need it, I want to add stuff like regex-based types. So you can basically optimize like the serialization using the like non-deterministic finite automata that you get from the regex. So you can only encode the state transitions as like a bit stream rather than encoding like the whole number in one shot, right? Because that's stupid. So it's sort of like an arithmetic encoding trick. But yeah, anyway, that's it. There's a lot of stuff I didn't talk about. I totally went way over my time limit. My apologies. This was, even then, this thing that was supposed to be a 10-minute talk ended up taking 20 minutes. So I think I'm good. I'll just like kind of leave this open to questions at this point, right? But there's a lot of other stuff in MuDB that I didn't talk about. But this is just the serialization component.
Super cool, man. Michael, do you have any questions?
No, that was really cool. I'm very excited about this regex type thing. That sounds pretty rad, actually. But like, you haven't actually built that yet, so like, I'm interested to hear kind of where that goes.
Well, I have a prototype for that I didn't merge into it because it's just we haven't needed it, right? It's like none of the data we have actually ends up being strings for the most part. So it's like, or when they are strings, they're just like strings of Chinese characters that are just full UTF-8 unencodable like mess, right? So, but actually the reason I wanted to do that was inspired by IPFS because our whole backend is built on IPFS, right? And so I wanted to actually try encoding the hashes using that UTF-8 thing, right? So you could do your base 58 encoding using the regex. So that was the original thing, but then it turned out to be just, you know, faster to just write a custom hash serializer for IPFS in it and just use that instead. But it would make sense, right? And then you could play around with like other hash formats if we ever did something other than IPFS.
Well, actually, IPFS supports multiple hash formats. There's this whole thing called multi-base.
Exactly.
But if you're working with the older style stuff, then you're always using base 58 BTC. Yeah.
Right. Well, what I was talking about is with the multi-hash encoding, it's a base 58 string, and then it has a prefix that's always like the hash ID, right? And then the multi-hash thing. So you could just write a regex to say, is this a multi-hash, right? And then the multi-hash regex would give you an optimal encoding of the hash. And then it also validates that it's a valid hash, right? So it's automatically done for you. Don't even have to think about it. It turned out, in China, you can just get someone to write that code for you without having to do the regex. So it's even faster.
So have either of you taken a look at web transport? I was wondering if that would help with making, you mentioned head of line blocking, and that was like a bottleneck. Wouldn't that still be an issue with your approach even if you're using a WebSocket?
Well, if you're using TCP, there's going to be head of line blocking, right? So I can actually comment a little bit about how we deal with that in our sockets. So we actually emulate unreliable transport over WebSockets, right? Which sounds really stupid. Yeah, but the way it's actually a good idea. It sounds like a stupid idea. It's like, why would you make TCP worse, right? But it's actually making it better.
You can literally do it. Like you can't like make it UDP. It's TCP, right? So what are you doing? Like, what are you doing?
You can, right? You can. There is a trick because basically what you can do is the reason TCP is slow is because it is reliable. So all you have to do is just make it unreliable, right? How can you do that? You open multiple sockets at the same time and you throw out messages. So the order of arrival is now non-deterministic, and sometimes messages don't end up there, right? So the question is then, okay, when do you send a message and how do you throw it out? Well, the way you decide this is very simple. You basically look at the bytes pending field on each socket, which is basically whether there's stuff buffered in the socket, right? And you just loop over all the sockets until you find the one with the least bytes pending. You just stuff it in that one, right? And then you go through them and you can just keep going through them. And if none of them have bytes pending, you just throw out the data and it works like UDP.
Wow. That's insane.
Yeah.
That's insane.
I could go on for hours with weird shit that's been invented to make this thing work. There's a reason there's not too many MMORPGs that use WebSockets. So I will tell you this, right? Especially real-time ones with rigid body dynamics that run at 60 frames a second in a web browser on a phone that's made in China from 5 years ago.
Wow.
Yeah.
Hopefully, Quick gets you some new things.
Yeah, that'll be great. Well, in a way, I'm actually kind of happy for it because we got it working now, right? And now I feel like all it's going to do is just make it easier for like our competitors to catch up to us at this point, right? So I'm actually kind of happy with it being terrible at the moment because it works for us, right?
Right. Well, web transport is basically Quick. I haven't looked too much into it, but it's basically a way to do like a quick socket browser in a safe way. So
it makes sense. And I like, for example, if you are using like a desktop app, we can just use like UDP and TCP and Electron, right? So if you're willing to like go to like extreme lengths, it's possible to make this stuff work. The real problem is like mobile browsers and like NAT firewalls. Like oftentimes, even if you have UDP, you still may need to use TCP just to do NAT traversal, right? So WebSockets, in a way, they're terrible, but in another way, they're great because they work out of the box anywhere. And if you can access the web page, you can do NAT traversal and all the other crazy stuff that has to happen just directly through the WebSocket, right? So it's simple. But with Quick, I think you also get all that stuff too, right? If you have Quick transport available. So like, I think it would be great if the web was designed from the beginning to have UDP as an option for a web transport. That would be so cool, but it just didn't happen like that. So we have to invent weird solutions to make this work.
I think that your story about your looping over a bunch of WebSockets to emulate unreliability is definitely the highlight of the mad science here. It's the most cool thing I've ever heard.
Oh, that's implemented in MuDB. You can actually use it out of the box right now. This thing is production tested under pretty significant server stress.
That sounds like the least production thing I would run. I mean, honestly, just
totally works, and it's awesome.
So, like, I was gonna ask. I know like a tiny bit of Chinese, but isn't Mu like emptiness basically?
It can mean multiple things. It literally means wood in this particular case. So it's like
okay.
wood. Like, the character Mu, it's a very simple character. I don't know.
Okay. Wood. All right.
Yeah.
Cool. Well, shall we go on to the social part of the event? Okay,
sure.
Cool. All right. Well, yeah, thanks again, guys, for agreeing to do your talks on such short notice. Like, we literally thought of this thing on Tuesday, and then we like made a whole entire meetup happen. So thank you. You guys made it happen. Super cool.
Yeah, thanks for putting it together. I haven't had a good chance to talk about this yet, right? Every time I send a talk, it just gets rejected. Probably because my slide.
No. Because you center-aligned all your code.
Yeah, I know. Oh, well. One day I'll figure out how to do left justification.
Cool. So what I want to mention now is just how we're going to do the next part of the event. So basically for the next 30 minutes, if y'all want to stick around, we're going to try a new thing that I've been working on. It's an app called Speakeasy, and it's going to help let us meet up with each other and talk to each other. So the way it works is you join the URL, and then you'll be matched with a random attendee who's watching the stream right now. And so I look at, what was that, Mikeal? Were you saying something?
No, I wasn't, but I was like, you said an URL, and then I didn't see an URL.
Oh, sorry. Yeah. I'll show the URL in a second. Sorry about that. Yeah. So anyway, you'll be matched with a random person watching the stream, and based on what I see on the stream right now, there's about like 40 people online watching. So at least on Twitch. So yeah, and then you'll be given an icebreaker question, and then the call will last for exactly 2 minutes. After which point it ends, and you get to talk to a new person. So it's like a little mixer, social mixer using the power of web technology and mad science. And then if you like the person you're talking to, you can also click extend. And if both of you agree to extend, then the call will go on for more than 2 minutes. So yeah, we're going to give it a shot. No idea how well this is going to work. It's an experiment, and it's in the spirit of mad science. So we'll see if this is a good idea. If you want to give it a shot, the URL to try it out is speakeasy.co/JS. So you should go ahead and do that in a new tab, and we'll see you there. And yeah, and I'll see everybody on that URL in a second. And I think the speakers are going to jump over as well. So if you're lucky enough to get matched randomly to one of the speakers, you can go ahead and ask any of the questions that you had that you didn't have time for in the chat. If we didn't have time to get to your questions. So yeah, go ahead and go there now, and we'll see y'all there. Thank you very much.
Yep. Bye.
Bye-bye.